Hello, everyone. I'm Chong from Princeton University, and my advisor is Professor Pratik Tom. Today, I'm going to talk about my PhD research on how to build certifiably robust perception models against adversarial patch attack. I will spend the first 10 minutes explaining what the research question is and why it is interesting and important. To start with, we all know that perception plays an important role in many interesting real-world applications. For example, face authentication on your smartphone. The objective is to recognize your face in the physical world. Autonomous vehicle or driving assistance. The car needs to first understand the physical surroundings and then make decisions based on that. Augmented reality, for example, for map navigation. The system needs to learn about the geometry of the physical world so that they can know how to place the virtual objects. As we can see, the functionality of these systems heavily relies on the ability to perceive the physical world. As a result, any perception failures could lead to a system breakdown. The most devastating example might be the autonomous car failing to detect objects and causing fatal accidents. We have heard the news about Tesla and Uber's autonomous assistants, for example. And this is not the only bad news. Researchers have found that attackers can even amplify all these perception failures, making them happen intentionally. For example, wearing adversarial glasses could impersonate others. Attaching stickers to the stop sign can change the classification prediction from stop to speed limit. For object detection, the adversarial t-shirt could hide the person from being detected. For lane detection, a dirty patch on the road can manipulate the detected lane for the vehicle. Given all these attack examples, in this talk, we are going to discuss how can we protect perception models from these attacks. As the very first step, we need to formulate the attack to understand what an attacker can do. We consider a threat model called localized adversarial patch attack. The assumption is that an attacker can only control part of the physical world, but not the entire one. Then, if we consider an image, the attacker could corrupt a localized image region, which looks like a patch. For example, given this image boundary, the attacker could corrupt this red region. Then, the attacker would optimize the patch content for any malicious purpose, for example, inducing misclassification. Now, the interesting thing is, given a victim object, the attacker can print and attach the patch to the physical object. The image taken from that physical scene could become malicious. For example, this stop sign with an adversarial patch on it can be misclassified as speed limit. And this is the formulation of the adversarial patch attack. Now, going back to these attack examples, we find that they can all be categorized as adversarial patch attack. The attacker only controls part of the physical world and introduce localized corruption. This adversarial patch attack is the first keyword of today's talk, the attack we aim to defend against. Before we start discuss any robust algorithm, there is always a tricky question. How can we make a rigorous claim about robustness or security? Note that security is always a dynamic game. Attackers, defenders trying to beat each other. As a result, we can see a lot of examples where the proposed defenses are broken by smarter adaptive attack within a few months of the release. In the literature, we can see papers claiming they can bypassing some defense methods. Some defense give a false sense of security, adaptive attack, a partial break on defenses, and evading adversary example detection defenses. Observing this cat and mouse game, a natural question we have is, can we somehow prove or certify the robustness of the proposed algorithm against unknown attack, maybe in the future, but within the same threat model? This would end the arms race between attackers and defenders. And here comes the concept of robustness certification. the second keyword of today's talk. The high-level idea is that given a defense model, an input image, and a threat model, which tells you what an attacker can do, for example, how large the patch could be, the objective is to generate a certificate which says the model prediction is always correct, no matter what a white box adaptive attacker within the threat model does. Here, white box adaptive means that the attacker can know everything about the defense, including the algorithm, parameters, model architecture, and model weights. The certificate needs to consider any attack strategy that follows certain constraints defined by the threat model. And a typical threat model used in the literature and also in this talk is we consider one square patch, and the patch should take up to 2% of the image pixels. Then the attacker can choose to place the patch at any image location. They can also choose to introduce any patch content for any malicious purpose. And our robustness certification needs to account for attack with all these different flexibilities. Now going back to our title. In this talk, we are going to talk about how can we achieve certifiable robustness against adversarial patch attacks. There are about 17 algorithms proposed over the past 3 years, and here I categorize them into 3 different groups based on their robustness techniques: bound propagation, small recept field, and pixel masking. In this talk, I will cover 2 techniques by discussing their most representative and powerful algorithm, namely patch guard and patch cleanser. I will briefly discuss the bound propagation technique at the end of the talk. So here is the outline for the rest of the talk. First, I will introduce the patch guard defense, which leverages the idea of small recept field. It is the most popular defense framework over the past 2 years. Second, I will discuss patch cleanser, which use a different way to achieve certifiable robustness, and it is the current state-of-the-art defense algorithm. After that, I will give a quick overview of the state of this research area, discussing the progress made and limitations left. Now let's start with the patch guard. Patch guard is a 2-step defense framework. First, it leverages small recept field to bound the number of corrupt features. Second, it performs secure aggregation on the partially corrupted feature for a robust predictions. We will show that with the proper design of these 2 steps, we can achieve certifiable robustness against adversarial patches. First step, small recept field. We consider the recept field as the region of the input image that an extracted feature is looking at. Take a convolutional network as an example. As we go deeper into the network, the convolution operations makes each feature in the deeper layer see a larger part of the input image. And a conventional network will extract features from different parts of the image. For example, the first features might be looking at this part of the image, then the second, third, and fourth feature can look at different part of the image. Gathering all these features gives the local feature map. Here, we call it local features because each feature only focuses on part of the image instead of the entire one. Next, the conventional network will perform feature aggregation to get the global feature representation, using, for example, average pooling. Here in this slide, I simply element-wisely add everything together. Now, given the global feature, the model can make the final prediction. In this talk, we consider a simple cat versus dog classification task. Here, the dog has high activation, so the model predicts it as a dog. The first key insight in patch guard is that the recept field size determines the number of features that can be corrupted by the adversarial patch. For example, if we use a network with large recept field, The small patch at the corner could appear in the recept fields of all features and corrupts the entire feature map. This leaves us little hope to perform a robust prediction. On the other hand, if we consider a network with small recept field, it could be the case that only 1 out of 9 feature is corrupted, and this gives us a chance to recover the correct predictions. Therefore, the first step in our patch guard design is to use small recept field to bound the number of corrupted features. This lays the foundation for our certifiable robustness. The second step is to perform secure aggregation on the partially corrupted features. Going back to this example, even though there is only one corrupted feature, a powerful attack can still introduce large malicious values to dominate the insecure feature aggregation, like average pooling. Therefore, we still need a secure version of the feature aggregation for robust predictions. In PatchGuard, we further propose a technique called robust masking, which detects and removes large feature values. The proposed technique leverages a concept called local logics. For each local feature that looks at a particular part of the input image, we can make local predictions based on the features to get a logits vector. Then each local logits vector also has a small recept field. We can repeat the same thing for all different local logits, and then we can gather the local logits map. Here, if we aggregate all these local logits vector together, we can get the same global prediction back. Our secure aggregation technique operates over the local logits map. Here, we will use a different visualization. We take each slice of the local logits map as a 2D matrix. Note that each local logit slice corresponds to one class. Here, the upper slice means for the cat, and the lower slice is for the dog. Then, the element within each slice represents the class evidence gathered from that region. Here, I also calculate the sum of class evidence for each class and put them below the local logit slice matrix. Note that the model will finally predict the class with the highest class evidence sum, and the cat in this example. Now let's talk about the algorithm. The first step is to clip our negative logits values to 0. We will see why this is useful later. The core operation is to move a sliding window over each local logit slice. Recall that the small recept field have bound the number of corrupted features, so we can use a window that is large enough to cover all corrupted features. In this toy example, we use a 1x1 window. Then, for each window location at each local logit slice, we will calculate the class evidence sum within that window. After we examine every window location, we will finally mask out the window with the highest sum for each class. Let's see a concrete example. For the cat local logit slice, we move around the window and identify the largest 30. For the dog slice, we will find this 7. Then we will mask out the 30 and 7 and recalculate the class evidence sum for each class. We find that the prediction changed back to the dog because the most malicious feature 30 for the cat is removed. Let's see another example in the clean setting when there is no attack. We find this 2 for the cat and find this 7 for the dog. After the masking, the prediction is still correct as the dog. This is because the class evidence for the dog is much larger than the cat before the masking operation. So this is how PatchGuard works, and it makes sense intuitively, right? But a more important question is, how can we certify the robustness? Recall that we aim to obtain a robustness certification. for any attack within a given threat model. So how can we get that certificate? We need to reason about the robustness in the worst case setting. In this slide, I will show that our patchguard design imposes an upper bound and a lower bound on the class evidence. To start with, due to the use of small recept view, the attacker can only corrupt and control features within a small region. And here in this example is the 1x1 region as the corner. Then we can claim that the attacker cannot increase the malicious class evidence too much because large values will be detected and masked. For example, in this cat slide, any values larger than 2 is going to be masked. So we will have an upper bound for the class evidence sum. Second, we can also claim that attacker cannot decrease the class evidence too much because we have clipped all negative values to 0, so the attacker can only push the malicious values to 0. So we have a lower bound for the class evidence sum. Then given an input image, we can calculate the upper bound and lower bound for all different classes. If we find that the lower bound of the true class dog is higher than the upper bound of any other class, we can claim that the defense will always predict dog. Then we repeat this analysis for patches at all possible image locations. If the same result holds, we can say the image is certified. The model prediction is always correct on this image against this threat model. And this is the last technical part of the patchguard design. Now we can discuss the experiment and evaluation. We focus on 2 metrics, clean accuracy and certified robust accuracy. Clean accuracy is the fraction of test images that can be correctly classified when there is no attack. Certified robust accuracy is the fraction of test images for which we can certify the robustness. Recall the pipeline of robustness certification here. We note that this certified robust accuracy is a provable lower bound on model accuracy against any future attack within the threat model, because we have analyzed the worst case attack. For the threat model, we consider a 1-2% pixel square patch with any content anywhere on the image. Here we discuss the results for the 1000 class ImageNet dataset. We consider clean accuracy, certified robust accuracy. This is the performance of prior and concurrent works of patchguard, and this is patchguard. We can see that the patchguard achieves the 5 to 10% improvement in clean accuracy and 1 to 2 times better robust accuracy. This is a notable performance improvement in the early attempts to achieve certifiable robustness against adversarial patch attacks. Moreover, we note that patchguard turns out to be a very extensible and powerful framework, using the 2 steps of small recept fields and secure aggregation. Many follow-up work use a similar 2-step design and propose different ways to implement small recept fields or secure feature aggregation. Going back to this figure, researchers have designed better models with small recept fields and significantly improved the defense performance. And this is what I want to discuss about patchguard, a popular 2-step defense framework. Next, I will discuss the second algorithm, patch cleanser, which is the current state-of-the-art defense algorithm. We just talked about the patchguard. Hope you were excited about its 2-step design. However, patchguard has a fundamental limitation. That is, the use of small recept field hurts the model accuracy. Let's see a simplest version of patchguard defense. We can crop the image into different chunks, make local prediction on different chunks, and then perform majority voting on local prediction to get the final robust prediction. Ideally, we hope all local predictions are correct. However, we can see that many image trunks don't see the dog at all. As a result, the prediction for those image trunks can be incorrect even without an attack, as shown in this example. To give you a more quantitative example, if we consider the ImageNet classification task, early defenses with small receptor field incurs a large clean accuracy drop from undefended model, for example, larger than 25% drops. This gap has been improved recently, but there is still a 10% difference. In practice, we don't really want to use a model that is partially broken even without an attack. A natural question to ask is, can we build a certifiably robust defense whose clean accuracy is in this blue region? Yes, with our patch cleanser design. It is the first time for any machine learning task that certifiable robustness doesn't have to cost the model accuracy that much. Let's see how we can do that. On the very high level, patch cleanser is a pixel masking defense. The idea is super straightforward. We're trying to mask out the entire patch to neutralize the adversary effect. Then, we can recover the correct prediction using any state-of-the-art image classifier, which usually have large receptor field. The challenge is, how can we mask out the patch without knowing where the patch is, and especially in a certifiably robust manner? Here, I will discuss some intuitions that inspire our defense design. First, we observed that applying small masks to clean images barely changes the model prediction because we can still recognize the dog even with a small mask on the image. On the other hand, when there is an adversarial patch on the image, applying mask will change the model prediction because when we mask out the patch, we can get the correct prediction back. Then we will see a disagreement in masked predictions. Now, given this disagreement, the question is, how can we settle it? Or how can we identify the correct prediction label? In this example, we might want to output the minority disagreement dog because we only have one mask that removes the patch. However, what if the attacker knows about our defense strategy and introduce different prediction labels? Note that the attacker still has control over other 8 predictions because the patch is not removed. Therefore, the attacker might be able to change this cat to fox and maybe move the fox around. Then, how can we distinguish between dog and this fox? An equivalent question is, how can we distinguish patch removing masks from other masks? Our solution is to add a second mask to different image location and analyze the model predictions on images with 2 masks. This would allow us to determine if the first mask removes the patch or not. Let me give you more intuition about this. Case 1, if the first mask removes the patch, then the second mask is applied to a clean image. Based on our previous discussion, masked prediction on clean image usually have an agreement. Therefore, in practice, if we see a 2-mask prediction agreement, it is likely that the first mask has already removed the patch, so we can trust these prediction labels. On the other hand, if the first mask doesn't remove the patch, the second mask is applied to an adversarial image, we will know that the 2-mask prediction will have a disagreement. Therefore, in practice, if we see a disagreement in our defense, we should not trust the prediction because there are still adversarial pixels left. Based on this difference, we can design an algorithm we call double masking, that is defense with 2 rounds of masking. First, we generate a mask set. The requirement is that at least one mask from this set can remove the entire patch regardless of the patch location. We discuss how to generate a mask set efficiently in our paper. Then, we will apply these masks to the image, check all one mask predictions. If there is an agreement, we believe it is a clean image, we output the agreed prediction. If there is a disagreement, we think it is an adversarial image, and we will trigger the second round masking to settle this disagreement. Note that the second mask is applied to every masked image from the first round. After applying the second mask, we will check the prediction agreement again. If there is an agreement, we know the first mask removes the patch, so we can trust the agreed prediction. On the other hand, if there is a disagreement, then there are still adversarial pixel left. We will discard this prediction label and move on to the next masked image from the first round. In our paper, we have additional details to ensure the algorithm will always return the label. And this is our defensive algorithm. Next, how can we prove the robustness? How can we do robustness certification? In our paper, we show that two-mask correctness implies certifiable robustness. That is, we consider all two-mask combinations from the mask set. If the model predictions on all these different two-masked images are all correct, then our defense is robust. We always predict the correct label. I would really encourage people to check out the proof in our paper. It's fun and doesn't need any complex math equation. Here, I will show some intuition for patch cleanser, never returning incorrect labels. There are two conditions that we can use to prove the robustness. First is at least one mask removes the patch, and the second is the two-mask correctness. This is our defensive algorithm. It returns predictions based on either one mask predictions or two mask predictions. For one mask prediction, here we can claim that there will be at least one correct one mask prediction. This is because at least one first round mask will remove the patch, and due to the two mask correctness, the model prediction on this masked image without adversarial pixels is correct. Then this correct prediction will enforce a disagreement with any other labels if there's any other different labels. So we will never return incorrect label in the first round masking. For the second round masking, we can do a similar analysis. We will know at least one two-mask prediction is correct because one second round mask will remove the patch. This will enforce a disagreement if there is any other label and ensures that the patch cleanser will never return incorrect label. And finally, because our algorithm will always return, more details are in the paper, and we show that we will never return incorrect label. So our defense will always return a correct label. Now let's talk about the defense performance on the ImageNet dataset. Again, we consider clean accuracy and certified robust accuracy. Here is the range of accuracy of undefended models, and here is the performance of prior works, and this is patch cleanser. We can see that the patch cleanser has a very high clean accuracy. It falls within the range of undefended model. And this is the first certifiably robust defense that maintain accuracy drops within 1%. In this figure, we can also see that the certified robust accuracy is even higher than the clean accuracy of prior work. Recently, there are some more defenses proposed, but we can see the performance gap is still large. All these results demonstrate the strength of our patch cleanser defense. Here are the takeaways from our patch cleanser defense. First, we propose a double masking algorithm. Here I want to note that it is compatible with any state-of-the-art image classifier that usually have large receptor fields. Also, it achieves state-of-the-art certifiable robustness, and it is the first to achieve a high clean accuracy. In the final part of this talk, I'd like to give a high-level overview of this research area. The discussion is based on our recent survey paper. We surveyed 17 defenses for different tasks proposed over the past 3 years, trying to understand what the research progress is and what our next step is. Here are 3 important takeaways from our survey. Some of them were briefly discussed before in this talk, but I'd like to highlight them again. First, we find that 17 defenses are only using 3 core robustness techniques. Second, we are excited to see defenses now can achieve certifiable robustness at a small cost of model accuracy. Third, there are still limitations, and the biggest one is the computation overhead. First, technique. We find that only 3 core robust techniques are used: bound propagation, small receptor field, and pixel masking. I will quickly go over each of them. The first technique, the bound propagation. This was originally proposed for a different threat model of global imperceptible perturbations. The idea is to bound the activation of every neuron in every layers, and the bound is computed based on the model weight and the bound propagated from the previous layer. In this example, the figure borrowed from other papers, the pink area is the adversarial region that the attacker can move the internal features or final logics around in the high dimensional space. And the gray area is the conservative estimation of the boundary of the adversarial region. Then the model is considered certifiably robust if the gray area stay for the gray area for the final logics stays on the right side of the decision boundary. The second technique, small receptor field, we have extensively discussed in the patch guard. The third technique, pixel masking, have been discussed in our patch cleanser design. Second, the progress. We have seen these figures a few times. The first major progress I want to note here is defenses are now scalable to large model and large high resolution image dataset like ImageNet and COCO. This is an impressive result because most machine learning paper with theoretical analysis or guarantees, they usually only apply to customized, simplified tasks or models, and they can only work for small models or small data sets. But here, our the certified patch defense can work on the large models and large data sets. Second, we're excited to see that patch cleanser demonstrates for the first time that certifiable robustness doesn't have to cost the model accuracy that much. Limitation. And we find that high performance defense comes at the cost of computation overhead. Here we pick 2 representative examples. The patch cleanser has the state-of-the-art defense algorithm, defense performance, but it requires multiple expensive model predictions on different masked images and incurs a large overhead. For example, 40 times more computation compared to undefended models. On the other hand, if we only consider defenses with one model feed forward, the best defense, PatchGuard, has a much worse accuracy performance. Here we can see a 3-way trade-off between performance, robustness, and overhead. For undefended model, it has 0 robustness. Patch cleanser, poor defense overhead. And PatchGuard is somewhere in the middle. Observing this, a natural research question is, how can we further balance and mitigate this 3-way trade-off? We believe it is a very important research question. Another limitation we find is most defenses are working on the simplest task of image classification. However, many perception applications are using a more complex task like object detection, semantic segmentation, and many other different perception tasks. Our group has made some progress early efforts and propose the only 2 certifiably robust algorithms for object detection. Feel free to check it out if you're interested. And we hope there will be more people working on these more challenging problems. Now, this is the end of the talk. The takeaway of this talk, we first discussed the patch guard that leverages the idea of small receptor field, and it is a popular defense framework. Patch cleanser uses a different way to achieve certifiable robustness and is the current state-of-the-art algorithm. We are excited to see certifiable robustness can be achieved with a minimum cost of model accuracy drop. And finally, there are some limitations, and one biggest limitation is the large overhead. We are trying to find ways to mitigate the three-way trade-off. Here, I also want to note that we are maintaining a paper list for both adversarial patch attacks and defenses, and we are also maintaining a leaderboard for certifiable robustness.